Hi, my name is Autumn Swain, and this is my Lab 3 circuits for Physics 2212. So the purpose of this lab was to predict circuits and how they act due to series/parallel resistors. This was used to explore resistors and capacitors and to have a safe experiment with circuits. And the results are that I1 and I2 will equal 0.0172 amps, and the prediction of the currents and voltage resemble the values calculated from the multimeter. So some fundamental principles that are needed are Node's rule, Loop's rule, and Ohm's law. Node's rule basically states that at any junction of the circuit, the total current flowing into the junction is equal to the total current flowing out of the junction. So whatever comes in will also have to go out. Loop's rule basically states that the summations of I should equal 0 in a closed circuit. So the total charge of potential should be 0. And then Ohm's law states the relationship between voltage, current, and resistance, and it basically establishes the foundation for circuits and electricity. So to start the lab, I must predict the current I1 and I2 that would be measured by the two ammeters in the display one, and I calculate it by adding the total resistance, which would be 47 and 100, as shown to be 147, and then rearranging the formula V equals IR. I was able to find that I will equal I1 and I2, and those will both equal 0.017 amps. So, some assumptions are also that we must assume that the resistance of the ammeter is negligible and that the resistance of the wire is negligible, as well as the system is the circuits, but the surroundings are everything else. So this experiment was done in a FET lab simulation with two ammeters, two batteries, and two resistors at first, and that is shown here, where I was asked to find the current of L1 or I1 and I2 that would be measured by the two ammeters, and on the right shows the initial circuit, and as predicted, it was roughly 0.0174. The current itself in the FET lab was rounded up, and when backwards the ammeter would read as the same number, it doesn't change. Then I was asked to replace one of the ammeters with a voltmeter and see what happens. And when I did this, the ammeter read as 0 amps because the voltmeter has such high resistance, it basically stops the current from going through, and it basically creates an open circuit. And the voltmeter reads 3V since there is no other voltage drop. So now I have to find the potential difference because we're looking for where the voltage drops across each part of the circuit. And to do this, we have to use Loop's rule as defined earlier and Ohm's law. So basically, I'm taking the Loop's rule formula, which is VB minus IR 47 minus IR 100 equals 0, because they must all equal to 0. So the resistors and the voltage must all equal to 0. And by doing this, I was able to find that delta VAB will equal 3 volts, positive 3 volts, delta VCD will equal negative 0.96 volts, and delta VEF will equal negative 2.04 volts, and the rest of them will equal 0 because they just will equal 0. And then that will abide by Loop's rule because it will all total out to be 0. And then this is a visualization of the gains and drops. As you can tell, the batteries add to the voltage current as shown through A and B by how it shoots up, and then resistors negate that and they drop the voltage down, which is why in C to D it drops and E to F it drops. It's also important to note that stronger resistors drop it faster. As you can see, by C to D it drops much slower than it does from E to F, and this is because it's a 47 resistor versus a 100 resistor. And the sums of all voltages add to 0 as shown by how before A and after G. So this demonstrates Loop's law, and this also explains the voltmeter reading. Since it had high resistance, it was very little current that went through it. Okay, next I had to find the transfer of flow, which was when I took out the voltmeter and replaced it with a strut bar and then placed an ammeter parallel to the resistor. Now, ammeters have very low resistance. And due to this, when you run a current through something where an ammeter is parallel to it, the current is going to go through whatever it sees as easiest to pass through, which was the ammeter because the ammeter is low resistance. So it's going to go for the low resistance rather than to go through 100 resistance. This causes the total resistance to become lower to 47 ohms because it's no longer passing through the 100 ohms, which changes I to be 0.06 amps. Next, I had to find the resistance of each of the circuit's elements. To begin with, we must assume a wire the ammeter have 0 volts voltage drops across, which was stated earlier. And then I calculated them by doing R equals VI. And so I calculated for the resistors 47 and the resistor 100, and then I did for wire ammeter. And R47 equaled 48 ohms, R100 equaled 102 ohms, R wire equaled 0 ohms, and R ammeter equaled 0 ohms. And this data may be slightly off due to rounding, but it still lines up with the calculated and the predicted. Okay, next I was asked to do RC circuits. And I was asked to do it with 10 ohms and 20 ohms. And basically what happens is that the ohms seem to dictate the time because the 10 ohms require 10 seconds to charge and discharge, whereas the 20 ohms require 20 seconds to charge and 20 seconds to discharge. So the higher the resistance, the harder it is for the current to complete its circuit. And to solve the RC values, we had to use the natural log of the voltage differential formula that was given to us. And by using this, I was able to predict the RC to be 6 because 30 ohms times 0.2 amps is 6. And then the experimental RC would equal the 1 over the absolute value of the slope, which is shown below. And that would equal 6.88 because the slope is negative 0.1453. And I was able to get that by putting all my charts on the graph with the ln v over v naught and time. And then the graph on the right shows my actual timetable and everything. So some potential error is probably mostly just human error in stopping the stopwatch because stopping a stopwatch right on time is really hard, as well as there was rounding errors because in the real world, everything works out to that decimal, but I had it rounded off. And so the numbers are slightly off, but they all are relatively the same. And then online simulations are not able to fully capture the real world scenarios. So the FET lab would not properly predict what would happen in real life in a more complex situation. So what if we were doing this experiment in real life and using an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how would it have affected the circuit you hooked it up to? If an actual ammeter was used, it would have resistance and limit the total current. This is because an actual ammeter is going to have much more resistance, and so it's going to control the circuit that it is in. And what if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacity to reach full charge? Without a resistor, the model would predict the capacity to charge immediately. This is because there would be nothing to stop it. However, in real life, batteries actually already come with internal resistance because you don't want something to charge immediately because that's like dangerous. So batteries in real life have internal resistance, which would stop it from immediately charging. However, in the FET lab, it would charge immediately because there is no resistance in the battery. And that is my lab for lab 3. Thank you.